Good evening, everyone. In this video, we're going to have a look at something called a conjecture and then work through an example of solving a particular conjecture example. Now, firstly, looking at the question, it says graph the following equations using digital technologies and then form a conjecture on the location of the turning point. So first point on the agenda is we need to know what is a conjecture. Now, the best definition I could find for it on the internet was a conjecture is a mathematical statement that has yet to be proved. And the second part, when a mathematical statement has said to have been rigorously proved, it is said to be a mathematical theorem. So what we've got over here in the purple is a conjecture is like an approximation of how mathematics could work, but you haven't proven it just yet, so we don't know if it's going to hold up in every single situation. Now, going back, let's think of a conjecture in that most of the time up until now in mathematics, when you've learned something new, you've always assumed because you've learned it in class, then it must be correct. But now what we're asking you to do is to be the, I guess you could say, the pioneers of mathematics. So we're wanting you to practice or role play in such a way that you're proposing a new mathematical theorem and you're going to go through all the steps that, say, someone like Isaac Newton or even someone like Euler, for example, some of the steps they've gone through to prove some of their theorems, or even Pythagoras per se. Now, to do that, as I said, it's a bit of a role play. So what we need to do is, looking at these equations here, we're going to graph them digitally. And as well as graphing them digitally, we're going to pretend that we've never actually seen these equations in our life before. We have no idea what their behavior will be like. All we know is that we just want to graph them and we want to find a general trend in the behavior of said graphs. So I've already gone ahead and I've put them into Desmos and plotted them. So what we've got is y equals x squared plus 2 is in the red. Notice the vertex or the turning point is at 0 and 2. Then y equals x squared minus 3. The turning point is down at 0 and negative 3. And y equals x squared in green. The turning point is at 0, 0. Now, going back over here, just for readability's sake, I'm actually going to graph them. So let's say 0, 2 is here. So y equals x squared plus 2 is going to look something like, not quite that, something like that. Mind the messy diagram, please. Y equals x squared minus 3 is going to look something similar to that. And y equals x squared is going to look something like this. So once again, I'm just going to reiterate, pretend that you've never seen these equations before in your entire life. This is the first time you've ever seen them graphed on a plane. Now, what we're looking for here is a common theme amongst all of these particular equations that might indicate to us a general idea of where the turning point is going to be. So looking at what's common is all of them seem to have a turning point at x equals 0. And the y value. So notice up here, x squared plus 2, it's at y equals positive 2, and x squared minus 3 is at y equals minus 3, and y equals x squared is at 0. So the conjecture for the location of the turning point as you probably figured it out by now, we could say that the turning point for equations of the form y equals x squared plus a constant is located at point 0, so it's always going to be 0 for x, and c, so the constant. Alright, so this little part here, this is our conjecture. Now the next part of the question is, or actually we'll go down once more and we'll revisit the proof or the definition of a conjecture. And we agreed that a conjecture is a mathematical statement that is yet to be proven. So going back up, this is definitely a mathematical statement. It seems to be okay for this particular family of quadratics. If there was, say for example, sake, if we had something like y equals x minus h plus k, if we had something like this, then this conjecture here, it's definitely not going to work, because this particular conjecture doesn't cover this form here. So say if there's another constant or another term inside with the x, it definitely won't work. So the conjecture itself only covers this condition here, so that's alright. So a conjecture is a mathematical statement that is yet to be proven. When a mathematical statement has said to have been rigorously proved, it is said to be a mathematical theorem. So part B, we want to have a look at our conjecture and prove it such that this becomes a theorem. So we said for our form y equals x squared plus c, the vertex is at 0c. Now what we'd need to do to be able to prove that this holds up is, firstly we need to prove that the vertex is always going to be at x equals 0, and then subsequently prove that when x equals 0 we're always going to be at a value of c, or y equals c. So the first thing I'm going to do is prove that the vertex is always at x equals 0. Now how could I do that? Well, simply using this equation here, we'll say y equals x squared plus c. Now if we consider what the roots will be in this particular equation, the roots will be at, or the roots of the equation are always going to be at y equals 0. So we'll say let y equal 0, and then 0 equals x squared plus c, then x squared minus c, and then we're going to get the square root of both sides. So notice we've got a negative in the square root here, but don't worry, it is plus or minus. So this would actually be a complex solution, but because we've got a plus or minus here, and we know that the vertex is always at the midway point between the two roots, we can say that actually let me just rephrase. So the vertex is always at alpha plus beta divided by 2, alpha being positive the square root of negative c, and beta being minus the square root of negative c. So vertex, we'll say x is going to be at square root of negative c plus negative square root of c divided by 2 is simply 0. So these two are going to add together to give a value of 0, which gives the vertex of x always at point 0 for this form here. Now you could easily see that simply by looking at the form, or you could have done this long-winded method here. So this one actually proves it algebraically. Now going over, since we've proven that the vertex is always going to be at x equals 0, to find the y value, by simply putting y equals x squared plus c, we can say let x equal 0. And then we can go y equals 0 squared plus c. 0 squared is nothing, and y equals c. Therefore, the vertex is at 0, c. So what we've done in this part B is we've proven a conjecture of the vertex being at 0, c for the form y equals x squared plus c. First bit we did was we found the roots, and it was a complex root, but because the roots are symmetrical across the y-axis, they cancel out, so the vertex is always going to be at 0. Then we used our vertex of 0 and subbed it in to the equation to solve for y, and we found that when x is equal to 0, y is equal to c, and because the x value of 0 is the vertex, the y value being c is the y value at the vertex, therefore the vertex is located at 0c, thus proving that the vertex is at 0c in an algebraic manner. Therefore our conjecture holds up. So that was quite a bit of work in the second section. If you have any questions in regards to the conjecture in general, so what it is, please let me know and I can make another video for the proving of the conjecture algebraically. So again, that was a little bit confusing because we had imaginary roots that we just worked with anyway. If that was a bit confusing, then not a problem. Let me know again, and either I can give another explanation of what was actually going on here, or we can do another question and see if that's a little bit clearer. But it's really important that you know how to follow this process for forming a conjecture and proving it, because you're definitely going to see it in the upcoming test on Friday and Monday, and you'll definitely have to know how to do this for SAYS. And it's not that it's new information, but rather it's just a process you need to follow. And if you can do this process, then pretty much it's just easy marks for you in the exam. So please guys, let me know if you need help. Otherwise, best of luck with it all.